Hey folks, how y'all doing? We're on the second day of our exam review. Um, this is the same slide that I started with last time. I'm just reminding people once again the exam is next Tuesday. Um, no, Tuesday the 15th, so not next Tuesday, the Tuesday after that. It starts at 11:05. There is a 50-minute multiple choice exam, and you have to take the exam at 11:05. You want to be logged into Canvas and um, start the exam at that time. So if you are in a different time zone, plan ahead to set an alarm or do whatever it takes so that you are taking the exam at 11:05 Virginia Tech time. Um, you do not have to use a lockdown browser. It is open notes, but you have 50 minutes to complete 11 or 12 questions, and you're not going to have time to finish if you're having to look things up. So you can use your notes, but think of them as a last resort. Really, really put the effort to having as much locked in up here as you can. So the second part of the exam is free response. You'll have until 9 p.m. that night to take it, so you do not have to take it right after the multiple choice part. You can if you want to, but if you want to take a break, you can. The two parts each weigh 50% towards the final exam grade. All right. If you have questions about the structure of the exam, let me know. I will try to get them answered for you. So this is the fall 2017 final. And let's go ahead and take a look at it. Which of these integrals represents the volume of the solid that lies between z equals x squared plus y minus 1 squared and z equals 2 minus 2y? So let's look at these. This is z equals x squared plus y minus 1 squared. Two of the terms are squared, one of them is not. One is linear. And the square terms have the same sign. And so this is an elliptic paraboloid. This is something from the early part of the semester. The vertex is at 0, 1, 0. And it opens into z direction. So sort of a quick and dirty sketch is it starts at the point y equals 1 and opens up like so. Okay. I'll do a more careful sketch for this in a moment, but I want to just sketch this part, and then let's look at this part. Z equals 2 minus 2y. When y is equal to 0, z is going to be 2. When y is 1, 2 minus 2 times 1 is going to be 0. So when y is 1, z is equal to 0. And since there is no x, that means that this shape continues in the x direction as far as we want. And so what we have is just a plane that goes through this line segment here. Okay, so it extends in x direction. So now we're going to combine these two shapes. And so this is where I'm going to try to draw this a little bit larger and a little bit more careful. Here's y equals 1. We know that is not just the base of the paraboloid, it's also the bottom of this plane here. The paraboloid opens upwards, and it crosses the z-axis. Well, the origin would be 0 squared, and 0 minus 1 squared would be 1. Okay. And the line segment that we're looking at for 2 minus 2y keeps going. It's up here. So we haven't found where they cross yet. So we could work back a little bit further. When we get to negative 1, then we have 0 squared. Negative 1 minus 1 is negative 2 squared would be 4. This would hit up at 0 equals 4. And 2 minus 2 times negative 1 is also equal to 4. So this is going to go all the way up to 4 and all the way back to negative 1. And that's where these two shapes cross. And then the paraboloid comes around from this. As the plane comes out from the paraboloid, I'm not drawing this very well. Maybe it'll help if I, drew the plane here in red. It'll cut through the top of this shape here, and then come down towards the bottom here. So we're slicing through at this corner and then cutting around this side and then around this side. Okay? And then we're looking for the shape that is underneath that up to this shape. This is a little hard to see, and I apologize I can't draw it better. Okay? But we now have to take all of this stuff and convert it into polar now that we've got all of this drawn out. So let's talk about what's going to happen here. So here's the origin. The radius goes out 1 unit, and we're going to go all the way around because this shape exists on both sides of the y-axis. So the angle is going to go from 0 to 2 pi, and the radius is going to go out 1 unit in both directions from the origin. Okay? And so now what we have to do is figure out what this equation is. The top equation is z equals 2 minus 2y. That's the same thing as z equals 2 minus 2r sine theta. And then the bottom function is z equals x squared plus y minus 1 squared. So that's going to be same thing as x squared plus y squared minus 2y plus 1. And so this is r squared minus 2r sine theta plus 1. And then when I subtract the top minus the bottom function, 2 minus 1 will be 1. And so we'll have 1r, 2r and 2r sine theta. These terms will cancel. And then we're going to have minus r squared. But when we're converting to polar, we have to multiply this by r. And so we get 1 minus r cubed. And so we're going to have this shape right here. 0 to 2 pi, 0 to 1, r minus r cubed. Okay? Oh, that was tough. Let's go ahead and move on. Let's suppose for a vector function r of t, we know that r prime is equal to 1, and that's r prime of 1 is equal to this vector. Sorry, not r prime is equal to 1. say that again, r prime of 1 equals this vector. And the principal unit normal vector is equal to this. What is the binormal vector when t equals 1? So we know that the binormal vector is t cross n. And we know that t is r prime over the magnitude of r prime. So they gave us r prime, which is 2, 2, negative 1. We can figure out what the magnitude of that is. That will be 2 squared is 4, plus 2 squared is 4, plus 1. Well, that's the square root of 9, which is 3. So that's 2/3, 2/3, and negative 1/3. Well, we also have this normal vector, which is negative 1/3, 2/3, and 2/3. They give us the 1/3 out in front. So the tangent vector is 2/3, 2/3, negative 1/3. The end vector is negative 1/3, 2/3, and 2/3. And so the binormal vector is the cross product of these. That's got to be 4/9 minus negative 2/9 is going to be 6/9. And then 4/9 minus 1/9 is 3/9, but we change the sign and make it negative 3/9. And then 4/9 minus a negative 2/9 is 6/9 again. And this reduces to 2/3, negative 1/3, and 2/3. And again, all of the answer choices have the 1/3 factor out in front. So we want 2, negative 1, and 2 in the center, and that looks like choice C. All right. So let's keep going. Number 3. Let f of xy be a function with continuous second partial derivative. This table above shows, wow, okay, so let's see what happens here. At this point, we have a critical point because the derivatives are equal to 0. So this is a critical point. This is not a critical point, and this is not a critical point, and then this is a critical point. Okay? So we have 2 critical points and then 2 other points that are listed, but they're not critical points. And so now what we know is that at this critical point, the Hessian matrix Hessian will be the determinant of this matrix. 3 is a concavity coefficient, 2 is a concavity coefficient, and then the mixed coefficient is the one that goes on the other diagonal. And this determinant is 6 minus 1, which is 5. A positive number is not a saddle point. And so the concavities are concave up. And so this point is a local minimum. All right, so then let's look at the other point. This time my Hessian is a determinant of 1 on this diagonal and 2 on this position, and then negative 2 along there. And this determinant will be 2 minus 4, which is negative 2, and that is a saddle point. Okay, and so we have a total of 1 local minimum and 1 saddle point. So That's consistent with this, no maximum, one minimum. It is not consistent with no local minimum. There's not one local maximum. There's not two local maximums. So that's what we found. It's not asking us how many saddle points we found. It's just how many extrema we found. And we only found one, and it was a local minimum. Okay? All right, let's keep going. Number 4. Which of these integrals computes the volume of the region that lies below z equals square root of x squared plus y squared and inside x squared plus y squared plus z squared equals 4? All right. So let's talk about what this shape looks like here. Z equals the square root of x squared plus y squared. If we square both sides, we get z squared equals to x squared plus y squared, which is the same thing as x squared plus y squared minus z squared is equal to 0. All of the terms are squared, but the constant term is 0, and that makes this a cone. And it's a cone that opens in the direction of the z direction. And since this is only the positive square root and not the positive or negative square root, we're only looking at the top half of the cone. Okay? The other shape, x squared plus y squared plus z squared equals to 4, that's a sphere of radius 2. All the terms are squared. That makes an ellipsoid because all of the signs are positive. So it's an ellipsoid, but because of the constant coefficients, we have an ellipsoid that's a sphere. So when we graph both of these together, we have this sphere. And then we have this cone that starts at the origin and interrupts inside the sphere. And what we want is this region that is below the cone and inside the sphere. So what we're looking for is this region down here, all the way up to the edge of the cone, but not the stuff that's inside it. Okay? And we have to set this up in spherical coordinates. Okay? So let's think about how we're going to do this. The order that we're integrating in is rho and then phi and then theta. So because we want the entire region and not just, let's say, like the first quadrant or something, we're going to go from 0 to 2 pi. Well, that doesn't help because all of my choices say 0 to 2 pi. They don't make the problems easy for us. So then let's talk about phi. Phi equals 0 is up here. And then this point is phi equals pi over 4. And then this point down here is phi equals pi. And so what we're looking at is, as a cross section, is everything from pi over 4 all the way down to pi. And that does help us here. That gets us the answer from D. Then the radius goes from 0 to 2, center from the origin all the way out to the edge of the cone. And 0 to 2 turns out not to be helpful, but we've already solved the problem by then. So let me spend a couple more minutes and talk about how do we get this middle value here. So I'm going to draw a cross section of what this piece looks like here. We have a circle of radius 2. And inside this circle, we have a cone. And the question should be, how do we know that this is exactly 45 degrees, or pi over 4? And it comes from the fact that these two coefficients are equal. That when, how do I want to describe this? So we're, for the example, this point right here that's on the circle, we know that the radius of the circle is 2. And so we know that x squared plus y squared is going to equal to 2 squared. And the intercepts then would be when x is equal to, how do I want to say this? X squared plus y squared is equal to 2 squared. It's the intersection of, here's a better way. It's the intersection of these two surfaces. And so what we have is S part is equal to z squared. And so we get z squared plus z squared is equal to 4. 2z squared is equal to 4. And so z is equal to square root of 2. And so the height right here is going to be square root of 2. And then at that height, if the z coordinate is square root of 2, then either of the individual values, if we do the cross-section along one of the axes, and we're just looking at x squared is equal to square root of 2 squared, then x would be square root of 2. Or if we're looking at y squared equals square root of 2 squared, y would be square root of 2. And so this point will also be square root of 2. And if this point is square root of 2 and this point is also square root of 2, then that's a 45-degree angle because it's got the x coordinate and the y coordinate equal to each other. So that's kind of what happens there. So this is a problem in which solving that middle coefficient is more important than solving either of the outside coefficients. All right. Let's move on. Please. Number 5, we're considering a circular cylinder. This is similar to a problem we did last time. We are looking at a circular cylinder whose radius is increasing at the rate of 2 centimeters per minute. So the radius is increasing at 2 centimeters per minute. And the height of the cylinder is decreasing. So the change in the height over time is negative 1 centimeter per minute because it's decreasing. Well, the volume, and they gave you the formula for volume. Volume is pi r squared h, and we're told that the radius is 4 and the height is 3. And so what rate is the volume increasing? In other words, how fast is the volume with respect to time? Well, this is a chain rule problem. The volume depends on the radius and the height, and they both change with respect to time. The volume with respect to radius is 2 pi rh, and the volume with respect to height, that derivative is pi r squared. 2 pi rh, where r is 4 and h is 3, is 2 times 4 is 8. 8 times 3 is 24 pi. And pi r squared is just 16 pi. So these are 24 pi and 16 pi. And we know that the rate of change of r with respect to t is 2, and the rate of change of h with respect to t is 1, negative 1. And they gave us that information earlier. And so the rate of change of volume with respect to time is 24 pi times 2 plus 16 pi times negative 1, or 48 pi minus 16 pi, which is 32 pi. And that will be choice B. Okay? Let's move on. What do the level curves of this shape look like? So the level curves are where the function is equal to a constant. So what we're looking at is e to the x squared plus 2y minus 4 is equal to a constant. I use k for constant here. Well, this is the same thing as saying that x squared plus 2y minus 4 is the natural log of a constant. But that's the natural log of a constant is still a constant. And then if I bring everything over to the other side, we'll leave the 2y. This will be negative x squared plus 4 plus ln of k. And so y is equal to negative 1/2 x squared plus 4 plus ln of k over 2. This is a parabola that opens down. Y equals something times x squared, and it won't start at the origin. Its vertex is going to be shifted up to this point here. But this is a parabola. And so that's choice 6, or choice D. All right. Number 7. Which of these statements is true? Is this the same problem that we did on the... it's worded a little differently, because the last time one of the choices was that something existed, and something about a kx in the choices. So this is a very similar problem to what we did last time, but it's worded a little differently. So let's look at some of these choices. If we look at the limit along x equals 0, we're replacing x with 0. Then my function will be 0 on top over 0 squared plus y to the 4th. And the limit as y approaches 0 of 0 over y to the 4th is 0. Well, that exists. And so it's not true that it doesn't exist. So then let's look at this other one. Y equals x, or x equals y, either one. Then your function f of x comma y will be x squared over x squared plus x to the 4th. And we want the limit as x approaches 0 of this function here. Well, that's indeterminate. That's 0 on top, 0 on the bottom. So we'll factor out an x squared. And now we have 1 on top, and we have 1 plus x squared. And 1 over 1 plus 0 is 1. And so this limit and this limit both exist, but they don't agree. And so that checks. We could go ahead and say that the answer is B and move on, but let's go ahead and check this one here. What if we substitute y equals x squared? Okay. Then we have f of x comma y will be x times x squared, which is x cubed, over x squared plus, since y is equal to x squared, this will be x squared to the fourth, which is x to the eighth. And the limit as x approaches 0 of that, the highest power I can pull out is an x squared. So that will leave me with x over 1 plus x to the sixth. And as x goes to 0, that's 0 over 1 plus 0, which is 0. And so this answer and this answer are the same. And so it's not true that they don't agree. They, in fact, do agree. And so that doesn't work. And since we've already established the limit doesn't exist, it can't equal 0. Okay? All right. Number 8. Let's see what we did with this one. Compute this integral. Okay? Well, this x cubed inside a square root with respect to x is hard to integrate. But y by itself is pretty easy to integrate. So what we would like to do is switch the order so that we can do the dy integral first and hope that that then changes the problem so that we don't have to do this hard integral anymore. So we'll start by drawing a picture. My bounds are y equals 0, y equals 1, x equals 1, and x equals y. So y equals 0 and y equals 1 are horizontal lines. X equals 1 is this vertical line here, and x equals y is this diagonal line. And since y and 1 are both bounds for x, the region we're looking for is the region in between. Okay? So now if we want to switch the order around to dy on the inside and dx on the outside, I need the largest and smallest x values, which are 0 and 1. And then the largest and smallest y values, if my arrow is moving in the y direction, we enter at 0, and we leave along this diagonal line, and y is equal to x along that diagonal line. And everything inside the function, inside the integral, stays the same. So this is the integral we want to work out now. So we'll start with this one, 0 to x of y times the square root of 1 minus x cubed dy. This is a constant, so I can pull it out to the front. And y I can integrate and get y squared over 2. Evaluated at 0 and 3. 0 and x, sorry. And we get the square root of 1 minus x cubed times x squared over 2 minus 0. So now the next integral we want to work out is the integral from 0 to 1 of the square root of 1 minus x cubed times x squared dx with an extra 1/2, and I'll take the 1/2 out to the front. We can do this with u substitution. We'll let u be 1 minus x cubed. Then du will be negative 3x squared dx. I need a negative 3 here. And since I don't have it, then just x squared dx is negative 1/3 du. Taking the 3 to the other side, it becomes negative 1/3. And so this becomes 1/2 times the integral of the square root of u times 1/3, or negative 1/3, du. And the boundaries have changed. The boundaries that were 0 and 1 are now 1 minus 0 cubed and 1 minus 1 cubed. And so they've switched places. So I'm going to pull out the square root of 1/3 here. Or not the square root of 1/3, just the 1/3, negative 1/3. I'll have 1/2 times negative 1/3 times this integral from 1 to 0 of the square root of u du. I would like to switch the order of this from 1, 0 to 0, 1, and I can do that by changing a sign. And so this is 1/2 times 1/3 times 0 to 1 square root of u du. Oh, all right, I'm running out of space, but that equals 1/2 times 1/3 times the square root of u. The integral of that will be u to the 3/2 over 3/2. And we're going to plug in 0 and 1. When I plug in 1, I get 1 over 3/2, which is 2/3. And when I plug in 0, I get 0. And so this, again, it ends up giving me 2 on the top and 18 on the bottom. I can reduce the 2's, and I get a total of 1/9.